Welcome to the first video in Search in a Nutshell. Today we're going to walk through essentially the introduction to search. So what is search, how we're going to represent search, how we kind of translate real problems to the framework of search, how we're going to draw up essentially the search trees, what the nodes are. Essentially, we're trying to cover everything about the foundations of search here in this video. So I've kind of drawn up kind of the list of what we're going to go through, so let's dive into this. So from the get-go, the whole idea here is that we are given some form of real-world problem, and we need to convert that into something that we can solve, right? Into some form of language, some form of framework, such that we can find a solution to the original problem. Your initial problem can be anything. So oftentimes we're dealing with problems that are sequential decision-making. So this includes things like route finding, navigation, right? So if you have a drone, a train, a person, a player, well, they need to go from A to B. Well, this is going to be a search problem, right? We can essentially reason over all the things that I can currently do from my location, and then every time I take a step, right, a sequential decision, well, where can I end up? What can I do? So forth. And we're looking for, essentially at the end, right, some transition from where you begin to whatever your goal is, okay? This does not have to be just navigation. The search frameworks are extremely useful just for logical reasoning and even solving things like a Rubik's Cube, right? So anything where you can define a state succinctly and then also define the actions that you can take, well, then we're entering into the world of search. So we have our initial problem, we have to convert it into states. So reminder of what a state is. Well, I'm going to use for this video just a standard grid map as our primary driving example. So a state is just a description of the real world, but with only the relevant, the pertinent information, okay? So it's like a succinct thing that we can actually use to perform search and to find solutions, but doesn't include all the additional information. If I'm trying to write a soccer playing agent, right? Well, your states may be the players' names. Hey, does Messi have the ball? Does Suarez have the ball? What actions do they have? Can they shoot? Can they pass? Things like this, right? But whether or not they're playing on a traditional grass field or a synthetic field, well, that is unimportant information to us. So that would not be included in your state. In a simple grid map, a state is just going to be your XY location. It's that simple. So the state corresponding to our start location S, well, that is just going to be the state A3 here, based on the coordinate system I've drawn up, okay? So states, I think, are very simple for everyone. Now, let's talk about why, though, we have to go one step further. We need to move not only in terms of describing the state space, right? So this is a polynomial domain. It's pretty countable, right? There's only so many places that we can be. Well, we're going to look at how we convert that to search, and we're also going to talk about how then, in that conversion, well, the problem starts to explode and become difficult. So why do we even go to search? Well, let's have a think about this. So let's say I've been doing some form of iterative algorithm and I arrive at the target E1 up here, okay? Great. I want to retrieve my path. So if I was just searching over states, I found the state, right? But obviously, you don't actually know how you reached this point. Order matters. Did you go all the way east, all the way north, all the way north, all the way east? And what about everything in between? So, of course, we as humans recognize that the order of your moves, right, the sequence of your actions, these have a large impact on the actual solutions you're achieving and essentially like where you are in the current environment. So we need a way to reason over the path so far, right, the actual order of moves, and this is where search and search trees come into play. So we're going to be searching over a node-based representation. We're going to be building a tree, right, starting from our beginning location S, our start location S, and trying to reach the target T. This is where the search space versus the state space argument comes into play, right? Order matters, I've just said this. So the domain itself is polynomial. This is pretty countable, it's nice. The search space is exponential. Why is that? Well, every single time I'm in a grid cell, I have some amount of moves available to me. I'm currently considering what we call a four-connected grid map. It just means I can move in just the cardinal directions. I'm going to ignore diagonals for now. That would actually make the problem larger. So I'm looking at a simple problem, even here, when you're at some form of state in the map, well, you have up to 4 available moves to you, right? You can go in 4 different directions. What that means for search is that my branching factor, as we'll talk about, the amount of things, branches, lines I can draw in my search tree is going to be up to 4. Instead of having just a countable set of states, instead of having 1, 2, 3, 4, 5, instead of having 15 states here, so 5 by 3, well, the amount of search nodes, the amount of options and permutations, right, combinations of all of your moves, well, this is exponential. This is why search is so difficult, and we're going to need good strategies in order to traverse the tree. It's not enough just to draw the tree. The tree is going to be extremely large for real problems. So we need good ways of dealing with that. That is where this entire field of study comes into play. So let's then talk about what are search trees and what are search nodes. How am I going to translate this state space problem into search? Well, so what we're trying to note over here, right, is we saw that order is important. This idea of knowing where we came from is important. So let's start then looking at what are things that search nodes are actually doing. What do they need to store? The first one is obvious. They obviously need to store the state it corresponds to, okay? So each search node is going to represent a location in your grid, yeah? So, hey, I have reached location B2. We saw that that is not enough information, right? You also need to know where you came from. Did I reach B2 from A2, or did I reach B2 from B3? So from the left or from below. So this is where then we also store a parent pointer. Okay, so we need to know which node, who is my parent, who actually created me, where have I come from. This will allow us to retrieve the final solution at the end as well. So this is exciting. When we reach our target T, we'll be able to essentially backtrack along all the parent pointers all the way back to our start location in our tree. The parent pointer implicitly has actions, right? It has actions. So the parent pointer, right, tells us where we just came from, and that also implicitly has the information now that I've added that is essentially what action you could have taken, right? So what named action, which direction did I move in that actually transferred me from this state to the new next state. Now, this is not the end of the story because we also need to start judging the value of our nodes, right? So when we're searching, we're trying to look for the optimal path, the shortest path. Well, that means that we are going to need a measure of the cost so far, right? So at some point in time, how long is the path I've already taken? So that is important for reasoning over the world. The final bit then is, you can write this in different ways. Textbooks do it a different way. I'm going to say it's just an evaluation function. Okay? Some textbooks say heuristic functions, some say depth of the node. Really, we need some way at the end of the day of not just looking at the cost so far, but we need to rank the node. We need to say how promising the node looks. Ta-da. So we have this idea of search nodes now. Let's talk about how we draw up the search tree itself. This is now going to be related to the idea of node expansion and generation. So when we expand a node, what it means is we look at our current node, our current state, and we see what actions are available to us. Even though this was 4 connected, you could technically move in 4 directions. There aren't always 4 valid actions available to us. Because we're in the corner of the grid, there's only 2, okay? So we have 2 options available. We move to A2 or we move to B3. Okay, so this is what we call an expansion. You expand node S, you generate its children. You add its children to the tree, to your frontier, the things we've found so far. Okay, so you would continue this as you go. From these positions, well, maybe you can reach multiple other locations, so forth. The branching factor, of course, could be up to 4 as we continue along. There are a lot of questions here that I'm not answering, right, in terms of, do you generate S again, right? Are you allowed to go back to the same location? So this is the idea of the search tree. This is why the search space is going to be so much larger. Well, there's 2 things that I've kind of already talked about. The search process we are going to need, right? These trees grow substantially large, right? We are going to need to find where our target finally is at the very end of search. when we're looking for our target T. The tree might be absolutely large, we might not be able to ever get there unless we choose to expand nodes in a nice way. That is what the search process is really doing, right? So we're essentially doing all these node expansions, we're choosing the order to expand nodes. This is leading us into the next video, which is going to be on search strategies, right? So a search strategy, the algorithms you've heard before, UCS, BFS, DFS, A*, all of these are just essentially an ordering. How do I rank nodes? How do I use my evaluation function? Which ones do I look at next? In terms of all of this, the final aspect that is here is this idea of duplicate detection, okay? So technically, when I moved from S to A2, I would be able to move back to S, right? We can have the same nodes appear in many subtrees, right, within the graph. This is starting to explode, and this looks dumb, right? We know that essentially we don't want duplicates. This is where the final idea of graph search versus tree search comes in. Well, standardly we use something called the open list. So the open list is going to track what we call the frontier. It's every node we've seen thus far, okay, but we have not yet explored. Well, essentially in this problem, we can also store something called the closed list, which will track the nodes we've already seen, okay? So when we have both of these lists together, so we know everything we've already found but we haven't looked at, and everything we've already looked at, ta-da, it means we can now start to prune duplicates from the search space altogether, and we cull their entire subtrees, right? We'd never have to explore these. This is the idea of graph search, okay? Graph search is just spending a little bit more time so that we can choose not to explore and to generate nodes we've already seen. This means that in graph search, we essentially only ever have one node for every state in the grid. And it means that when you find a better path to a node, right, that already exists, well, you're going to update its cost appropriately. In tree search, we don't bother there's no updating, there's no pruning, it's just you arbitrarily add in everything here, and then you'll eventually find the solution in the same way. So graph search is what we use moving forward. Okay, so that is essentially the foundations of search. Yes, it's a 13-minute video, but this could be 2 or 3 weeks in your foundational Masters of AI subject. So I hope you like this. Please stay tuned as we start to explore in the next video all of the basic search algorithms. We're going to be looking at BFS, DFS, UCS, DFID, and maybe even working towards the greedy best first search in A*. See you there.